Okay, right, we're ready. Welcome again, welcome to the conference. It's my pleasure to introduce you Professor Grande from the Norwegian University of Science and Technology, who will speak about defects in oxides. Please welcome together with me Professor Grande.
Thank you very much for the introduction, and also thanks for the invitation to give this tutorial lecture. So good morning everybody, hope you had a nice sleep and a safe travel to Lausanne. I arrived quite late yesterday, so I also had quite a nice sleep. So the topic I was given to give on a tutorial was defects in oxides. And the outline of the talk is the following. I'll first go through the typical defects found in materials, not necessarily specific for oxides, but that's for all type of materials. And the difference between these is the dimensions from 0 to 2-dimensional defects. Then I will go to point defects in oxides and use the Kröger-Fink notation in order to give them a systematic name with respect to charge and so on. And then I will talk quite a lot about the origin of these point defects in oxides, how they appear and so on, and also if it's possible to control them. Then I will link the point defects to the transport properties of materials, meaning that they are quite linked with especially the conductivity. And then I will go to some examples in the end, and I'll try to sum up in the end. I believe in tutorials it's allowed to ask questions. In any way, I would answer or try to answer if you have questions during the presentation. So don't be afraid to interrupt with the questions. So before we start, I guess many of you already know that the defects are important in solids, and especially in this community we know that they are also detrimental for the electrical, for the electromechanical, and also for the functional properties in general. If you're talking about ionic conductivity, for example, point defects are actually paramount for the ionic conductivity. You cannot high ionic conductivity without point defects. And the normal way to control that is by what we call compositional engineering, meaning that we are tuning the composition of the overall composition in order to enhance the ionic conductivity. Then we also have electronic conductivity in oxides. Typically, if you have cation non-stoichiometry, this is not so well understood in the community. And one of the key things here is to control or to look at the oxygen non-stoichiometry because of the cation stoichiometry. They are of course linked to each other. Then we also know that there are interactions of domain walls with defects or domains. And again, which is one of the big issues in this community is aging and fatigue in ferroelectrics, which also is quite related to point defects. All this is kind of problematic in a way, but there are also possibilities that you can use point defects or functional ionic defects in order to obtain new functionalities. And this was a feature article in Science by Kalinin and Spalding trying to emphasize this opportunity, that you have a possibility to also use functional ionic defects in order to obtain new functionalities. Okay, so that was a short introduction to why point defects or defects are important in general in oxide materials. So if you look at defects in solids, we can start to distinguish them between the dimensional. So if you start with a point defect which has no dimension at all, it's a 0 point or 0D. That's typically a vacant site in the lattice, or it can be a dopant or aliovalent element on the lattice sites. And this is typically illustrated by the Schottky and Frenkel defects in ionic solids, which is the most common, shown in this figure to the upper right corner, up here. And I will come back to the Schottky and Frenkel defects in a moment. Then we have one-dimensional defects called dislocations, and they are quite well known, particularly in metallurgy. The mechanical or the ductility of materials is very dependent on this kind of dislocation. And the two classical dislocations we can kind of distinguish is the edge dislocation, which is illustrated here, and the screw dislocation illustrated here. And this is in a way, if you look at the edge dislocation, it looks like you have one plane of atoms which is kind of squeezed in between two in a perfect situation, and then the new plane, if you speak, is then ending in here, so you can follow it into the crystal. So you see, if you count the number of atoms on the bottom and the top here, you see there is a difference. And the difference is due to this edge dislocation. The screw dislocation is where you kind of screw or you twist the two planes relative to each other. So, and the way you characterize these kind of dislocations is by this Brouwer vector, which is given also in the figure. I will not spend much time on dislocations, unfortunately, because it's not so well known, but I give a few comments on it later on. Then we have the maybe most common defect we all are quite familiar with, at least if you will work with bulk materials, and that is grain boundaries. Because you cannot make bulk materials if you don't have a single crystal, you always have grain boundaries in your sample. And this is illustrated here in a nice two-dimensional image of a grain boundary. This is actually in soap bubbles, which are make regular lattice, as you see here. But if you organize them not in one specific way, you have to have a grain boundary in between each grain. And grain boundaries are quite common. That doesn't mean that we understand them very well. Then we also have stacking faults and twin boundaries and other things, which is also two-dimensional in nature. Grain boundaries is also two-dimensional in nature. So this is the type of defects we are talking about in oxides. And all three of them also exist in oxides, but the way we understand them is not necessarily on the same maturity level. So if you start with a few words about dislocations. Dislocation is less frequent in ionic solids compared to metals. That's an interesting topic by itself. I will not cover that to a large extent, but for example, we can introduce dislocation induced by stress, which is typically also found in metals. If you do hard work hardening and so on, you introduce a lot of defects in dislocations in metals. And the same things apply also to oxides, which is ionic in nature. If you apply stress, you will also induce dislocations. But maybe the most common dislocation we can find in the oxide community today is this edge, or the dislocation you can see in thin films, where you have a mismatch in lattice unit cell dimension, and then you get a dislocation on the interface between the two materials. It's starting to be a larger and larger interest in order to understand what the dislocation means with respect to the functionality. And one of the things which has been studied quite a lot lately is transport along those dislocations in different oxide materials. And this has become because of all the interest in meristic, where edge dislocation are important. So, for example, this is an example of a dislocation in a typical perovskite material, where we have shown that the chemistry going on at the dislocation is quite different from the bulk surrounding the dislocation. For example, it is easy to reduce transition metal ions sitting on the edge dislocation, but it's not so fast. It means that in some way ions or defects are kind of pinned to the dislocation. Many have tried to predict that maybe the dislocation would actually represent a path where ions move faster, but it's actually been shown to be slower. So this is a topic now studied quite a lot all over the world, but I will not go back into more details on the properties of dislocations. Then we go to grain boundaries, which I said that's quite common, and grain boundaries is always present in polycrystalline solids. And one thing which is quite obvious, I guess, is that if you reduce the grain size, the density of grain boundaries increases. And if you go to nano region, this is nicely illustrated in a metallic system, where you see the volume fraction of the the grain boundaries given in this line here, and the triple junction as a function of the reducing grain size. And as you see, if you go from, and this is in nanometers, and when you pass, let's say 10 nanometers or so, you see that the volume fraction of these two-dimensional defects actually start to dominate over the bulk volume fraction. So of course, when you are finite size, you go down to very small, finite size, the effect of grain boundaries become even more enhanced, and of course, in some cases, it will, the properties will completely be controlled by the grain boundary properties. But the way we normally understand materials is that we understand the bulk, and we don't really understand the grain boundaries to the same extent. So I will also not spend more time on grain boundaries, but just illustrate for you a few examples how important it is to understand also grain boundaries. And one of the most obvious things is that the transport properties of grain boundaries is different from bulk. And this is not a new phenomena in oxide community. This is very well known in many of the conductive oxides, where normally either the grain boundary is beneficial to the transport properties, or it can actually also be a disadvantage. One example of this is the enhanced diffusion of ions along the grain boundary. Is it working? Yeah. So this is a Sims image taken of a typical ceramic material where you do O18 tracer diffusion, and you see the grain boundaries very easily in that image. So the contrast here is actually the concentration of O16 and O18 in the image. And along the grain boundaries you see that the diffusivity is much higher than in the bulk. Obviously that the oxygen, which is mobile in the system, is actually transported along the grain boundaries in much more extended state, or much more extended than in the bulk. Another issue with grain boundaries is that in some cases it also has a resistance, a grain boundary resistance, and that is not a general way of explaining that resistance, but one way is to look at space charge at the grain boundary. And here is a kind of a sophisticated example of that, showing, but in this case the grain boundary is actually a surface. It's not a grain boundary, it's the surface against air. And the important take-home message is that the grain boundary or the surface is actually charged relative to the bulk. And due to this charging of the grain boundary or the interface, if you speak, you get trapped some specific elements depending on the charge of the grain boundary or the surface, and that will then enhance or decline the mobility along the grain boundary. In this case, it's protons which are trapped. This is a proton at the surface, and this is trapped at the surface, and it means that because of the high concentration of proton at the interface here, the transport across the interface is actually quite problematic. So the activation energy is higher. And here you have used point defect modeling in order to see how the concentration of the different defects is then changing as you go from the interface and towards the interior. So this is due to the space charge related to the charge of the grain boundary. But again, I will not go in detail with respect to grain boundaries, not because it's not interesting, but the point here is we don't really know in general terms how grain boundaries will affect this. We have to look more specifically in each case. Okay, then let's move to the point defects in oxides. Then we normally try to distinguish between what we call intrinsic and extrinsic defects. You can only discuss how you put a border between intrinsic and extrinsic. But the two most important intrinsic point defects in ionic systems is Schottky and Frenkel defects. And the Schottky defect means simply that you actually have two vacant sites in the normal lattice. So if you, for example, in this case, have a rock salt structure where you have equal numbers of cations and anions, a Schottky pair means that you have one vacant cation site and one vacant anion site together. A Frenkel defect, on the other hand, is that you displace one of the cations or anions relative to the equilibrium position. So in the Frankel defect shown here, you see that you have one empty site. In this case, it's the red one which is missing, and it's then displaced to a so-called interstitial position. So meaning that you can move the ion from here up to here. And the two together, that is the Frankel defect, meaning that you have one vacant site and one interstitial site. And this can happen both on the anion and on the cation sublattice. So, but the problem here is that you cannot predict per se which of these ones will dominate in one specific system. This is something you have to investigate. So that is the intrinsic one. Then you have the extrinsic, which is normally due to either doping or because we have problems to obtain sufficient purity of materials. So impurities will also, in this way, work as point defects or in the same way as doping. And we normally distinguish doping by acceptor or donor doping. And I will come back to illustrate the difference between a donor doping and acceptor doping. And the name comes back from the semiconducting community. For example, if you have a silicon semiconductor and you put in boron and phosphorus, which has a different valence state than silicon, you have on one hand a donor doper giving away an electron, and an acceptor doping, accepting one electron. And in oxides we have adopted the same terminology, although it doesn't really mean exactly the same thing. So one example of an acceptor doping is gallia in ceria, gallium oxide in cerium oxide. And ceria has 4-valent in this case. And you can find that out from the number of oxygens. So the ceria has a 4-valent oxidation state. Gallia, on the other hand, has a 3-valent oxidation state. Also we can identify from the stoichiometry 2 to 3. And when you put gallia into ceria, you then have what we call an acceptor doping. And the consequences of that we will show in a moment. On the other hand, if you then dope an oxide with a higher valence state, you donor dope. And the classical example is niobium in strontium titanate. And maybe some of you are working with thin films, and if you have niobium doped in strontium titanate as a substrate, you change the substrate from being an insulator to become a metallic conductor, just by doping with niobium. So this is the intrinsic and the extrinsic point defects we can distinguish. In order to have a nomenclature, at least I'm a favor of this Kruger-Fink notation. And this is not used consequently in the literature, and that is also to some degree confusing because it's sometimes tricky to understand what we really mean with all different notations used for the defects. In the Kruger-Fink notation, the most important thing is that you are defining the charge of the defect relative to the site that it occupies. So everything is kind of labeled with respect to the ideal lattice. So for example, if you have a vacancy on the X, this is M2 plus X2 minus. So it's a rock salt structure where you have a divalent metal and a divalent X, could be oxygen, for example. So if you then have an X vacancy, we then distinguish the vacancy by putting V here, and then you put a subscript X, meaning that it's a vacancy on the X lattice point. And the two dots here illustrates the charge of this point defect. It's positively charged 2 times because of the relative charge of the ion in a normal situation. If you have an M vacancy, a metal vacancy, it's also given by the V on the M side, but then with the 2 negative charges, because it is negatively charged relative to the ideal lattice. And if you have a Schottky defect, which I will show in a moment, you see that the sum of these ones gives 0 charge. Then you can also have these M interstitials. Again, it's M on the interstitial site. Again, it's charged because there are normally nothing on an interstitial site. And then if you put an ion there, you will give it with the correct in this case the correct charge because it is positively charged in an isolated state. If you have a donor on the M site, again you get a donor negatively charged relative to the M, and an acceptor on the M site, again on the M site, A, and again a positive, sorry, a negative charge relative to the normal lattice site. All these defects is now illustrated in this rock salt structure where you can see all the different type of point defects given in the lattice. So it's also important to note that DNA, the donor and the acceptor in this case, has a different charge than the M. That's the whole point. So if you are doping with an oxide with the same oxidation state or the same charge, you only have a donor at the M site and then X on the normal side, and you don't really change much the defect chemistry. And this is very nicely illustrated in this review paper by Tuller and Bishop a few years ago. So if you now try to summarize what we have learned now, is the charge of the defect is relative to the site that occupies. If you have an M2O2 and an oxygen vacancy is given by this symbol, where the charge is now positive charge relative to oxygen anion, so which is negatively charged. The vacancy on the M site, on the metal side, is then negatively charged relative to M cation. And if you now go back to the Schottky defects and the Frenkel defects, we can now write a so-called defect equilibrium. And that's the funny thing here. You start with nothing, and you end up with two vacancies. Seems a bit odd first time you see it, but this is the way it is. You start with nothing, and you create two point defects by making a Schottky defect. And the Schottky defect is the sum of these two together. The Frenkel defect, you also start with a perfect lattice, nothing, and then you displace one of the ions from a normal situation, creating a vacancy with a charge, and then you have the metal at an interstitial site with again a charge relative to the oxidation state of the metal. If you look carefully here now, you see that both of these point defects, they don't create or annihilate any charge. So the principle of electroneutrality is very important when you talk about point defects. If you take the sum of the charges here, in both cases, the sum of the charge is zero. So one defect is counterbalanced by another defect. That's always the case, and very, very often neglected in the literature. Very important point, and I will come back to that in a moment. If you now look at how we can control point defect chemistry or the populations, they are influenced by several important factors. So if you look at the intrinsic defects, the Schottky or the Frenkel defects, the most important is temperature. And why is it so? All these intrinsic defects, they are entropy. Entropy is the reason why they are created. They are enthalpic, not stable, because you have to pay a price in order to make the defects, and that's the energy. So you need entropy in order to create them, and it's the entropy which is the driving force for creation of point defects. And that you can, of course, tune by temperature. The higher up in temperature you go, the more intrinsic defects you will have. Since this is also related to chemical potential, you can also change the concentration of them by playing with the chemical potential. And the most common one is to play with the oxygen partial pressure. Then you don't necessarily influence the concentration of all kind of defects, but they will be. You can also illustrate this later on. I will see put up a point defect equilibria for how the partial pressure oxygen will play a role. And then is the third thing, which is maybe the most complicated and less understood, and that's the relaxation time for point defect equilibria. That's related to the thermal history. And this is dependent on the length scale and the diffusion. Because you have to you're moving point defects in and out of the lattice. And that has a finite time scale, also that process. And this is again related to the length scale of the problem and also diffusion coefficients, which I will come back to in a moment. Maybe the most important thing from an engineering point of view is that you can control the point defect population by extrinsic defects. And that's what we normally do if you want to control, for example, the oxygen vacancy concentration. You do that simply by concentration of dopants. And you dope so heavily that the extrinsic defects will completely dominate. And then the intrinsic defect doesn't really play a role. But in most cases, for example in ferroelectrics, you don't want defects necessarily. And you don't have any dopants. And it's not so easy to control the concentration of the different point defects. A second or the third example of fourth is volatile oxide, which is really a huge issue in the ferroelectric community. So when you make a ceramic material, for example, you normally try to make the correct nominal stoichiometry, and you use the nominal amount of the different reactants. But the problem is one of them are volatile. You never end up with the stoichiometry you're aiming for. And this is a huge issue in many of the most important ferroelectric materials we are working with. And I'll come back to that in a moment. And then the last but not least, maybe one of the most important and critical issues is the cation bond stoichiometry. Because when you are a student, you learn the correct stoichiometry of a material. You read that, for example, barium titanate has one barium and one titanium, always. Because it's written like that. In reality, we know it's not like that. But we never write it. And it's normally always neglected in the literature and often also in the community. So if you make your own barium titanate, it's most likely that you're not able to reproduce what people have done before, because you're not able to have the same precursors with the same chemistry, with the same impurity level and so on, in order to control that the barium to titanium ratio is actually 1:1. And that's a really important thing with respect to the functional properties. Unfortunately, not very often focused on in the literature, because it's difficult and you don't know. And things you don't know, you don't write. So this is a very important thing. Okay, now I'll try to explain this, how this can be changed by temperature or thermal history. And I will keep to a quite simple example, is magnesium oxide. That's a very refractory oxide which doesn't really have much of an interesting functional properties, except that it is a transparent insulating oxide with a high band gap. But it's simple and it's easy for the purpose of illustrating what I'm trying to illustrate now. So if you look at the dominating point defect in magnesium oxide, that's the Schottky defect. And again we have the Schottky defect equilibria, where you go from nil to one vacant magnesium side and one vacant oxygen side. And you can write a very simple chemical equilibrium for this. So you have an equilibrium constant for the Schottky equilibria, and that's simply the concentration of the two vacancies multiplied. And the whole defect equilibria is then the free energy of that one is then controlled by the enthalpy of formation of the Schottky defect and the configurational entropy of the defects, dilute defects on the two lattices. And you can, from statistical mechanics, quite easily calculate the configurational entropy. That's not really difficult to do. I'm not sure it here. Maybe it's not the wise thing to say that thing is simple, but this is not too difficult anyway. So if you look at this equation, you see that as you go up in temperature, this becomes more and more negative, meaning that the Gibbs energy becomes more and more negative, or less and less positive, meaning that the concentration of these two are increasing. And if you look at the Gibbs energy as a function of defect concentration, you can then find the equilibrium concentration versus temperature. And if you go up in temperature here, you increase the temperature down here, you see that the concentration of the point defects increase. And the interesting thing here is that you can see that the number of point defects is actually quite real in a way. They are not so dilute. This is defect concentration in fraction. So you see that you actually have quite a lot of defects even in a ionic system like magnesium oxide. I did not put on temperature, but it is quite high temperatures. It's not room temperature. But still, there is an evolution of more and more Schottky defects as you go up in temperature. So, if you then have a magnesium oxide sample, one of the things you should ask yourself is what is the thermal history of that sample? Because that will tell you where you are in that landscape with respect to concentration. Population increases with temperature because of the entropy effect. But the point here is that you often freeze in a specific point defect concentration at the temperature of the process you have been processing your sample. And this is because of the diffusion kinetics. So if you look at this specific phenomena, we can illustrate that by having a grain or a ceramic sample or even a single crystal to a surface. So what's happening during heating is that the creation of vacancies, and the vacancies has to diffuse from the surface and into the interior of the material. So that's why it is a diffusion control process. When you cool the sample, you go from a high concentration of point defects to a lower, meaning that you have to annihilate. So this annihilation of vacancies, and the diffusion process is now in reverse. You have to diffuse oxygen and magnesium oxide vacancies from the interior of the sample to the surface, or to a grain boundary or something. So it's a diffusion process, and you can then illustrate how this will happen by itself just by looking at the thermal energy. So if you try to explain this, you can then take the diffusion constant. I will come back to how you derive this, but this is the diffusion of the vacancies as a function of an activation energy. And it's a thermally activated sample, so it's a simple Arrhenius equation. And the time it takes to diffuse for the length L squared is then can be calculated from this simple equation here. T is equal to 4 L squared divided by D. So it's not a very difficult task to calculate the relaxation time, how long time it takes before a new equilibrium is established if you go from one temperature to the other. So if you now have a magnesium oxide, let's say it's a single crystal, and it's 1 centimeter in length scale. This is the time scale it takes before you get equilibrium. And this is in minutes. So if you have a large sample, what happens? You are not able to influence on the concentration of the vacancies. It just takes forever. If you downscale the sample, you see also that the time scale goes down significantly. It's not and you see that from this relationship here. The length scale and the time scale is not a linear relation, but it's L squared. Meaning that this is something which is very dependent on dimensions. So as you go down here now, and you start approaching, let's say, nanoscale, you suddenly see that also the time scale becomes real. The time scale of the life we are living. The time scale of our life. And if you now take a 1 hour process, which is not realistic in a lab scale, you see that you can actually obtain equilibrium for samples maybe up to a few nanometer in size at different temperatures. Yes. But you lose then the equilibrium at 800 degrees centigrade. And if you go lower than 800 degrees, even the sample is very small, you still don't have the possibility to manipulate on the concentration of the defects. And this is what we call this freeze-in. And more often we are up here somewhere, and we neglect this. So the only thing you then are interested in, or should be interested in, is the temperature where you process the sample, or where the single crystal were grown. Because when the single crystal is growing from a melt, it will grow with the equilibrium Schottky defect concentration. So the effect of thermal history is important. Take-home message here is that this is much, much more important on a nanoscale than in typical bulk materials. So try to summarize that. So if you have a bulk ceramic, the concentration of point defects is determined by the level of dopants, impurities, which you never can avoid, and the sintering temperature. The sintering temperature defined where you kind of fix in the microstructure. And normally, if you change the temperature after the sintering, it doesn't really matter. You cannot influence on the distribution of or the concentration of the point defects in a significant amount If you're not clever, you can, but it's difficult. Normally you can neglect it. So it's less influenced by the thermal history of the chemical potential gradient due to slow kinetics of point defect equilibrium. So it takes time, and normally you can disregard any changes. Meaning that the intrinsic point defect concentration is more or less constant, and it's something you don't need to take into consideration if you see an effect of other things. But the concentration of point defects in thin films, for example, is sensitive to variation in temperature and chemical potential gradients. So then the synthesis condition is quite important, and also strain effects will also influence on the point defect equilibrium. I will not cover that today. Then I will go to the possibility to use a chemical potential or atmosphere, if you want, to control the point defect equilibrium. So if you take the transition method, they may change oxidation state at elevated atmosphere. It should not be elevated atmosphere. It should be a different atmosphere. The thermally induced reduction of transition metal and formation of oxygen vacancies. This is explained by the example of Syria. So if you take Syria and you expose it to a reducing atmosphere, meaning a low partial pressure of oxygen, you will then have an oxygen on an oxygen site, which is given X by, because it's neutral compared to the ideal lattice. You will then create two electrons, oxygen vacancy plus oxygen gas, meaning that you are sucking out oxygen from the lattice. Again, you see that there is a sum of the sum of the charge of the point defects are 0. So the point here is that you observe you will get an electronic conduction in Syria if you then go to reducing atmosphere. And that is also quite well known, that Syria becomes a mixed ion and electronic conductor under reducing conditions. And this is one of the main problems with Syria as an electrolyte in solid oxide fuel cells, because you get an electronic conductivity on the reducing side. And in an electrolyte you need only one charge carrier. So but again, there are also beneficial properties of this mixed conduction. Normally, this is really hard work to find out the defect concentration as a function of partial pressure oxygen. And luckily somebody have done that before, so I didn't need to do all the hard work. And this is the end of the story. It's a lot of work behind this, and this is called the Brouwer diagram, showing how the concentration of the defects is varying as a function of the partial pressure oxygen at a constant temperature. So this is isothermal data. So what you plot here is the logarithm of the concentration of the different point defects, and then you have the logarithm of PO2 on the x-axis. And normally your air or pure oxygen is somewhere up here. And depending on the dopant level and the partial pressure of oxygen, you will have regions of PO2 which is dominated by some specific point defects. Again, you have to remember that all the point defect has to be charge compensated in some way. So if you look here, is the principle of electroneutrality given in these different regions. So if you now go to very, very reducing conditions where this point defect equilibria is really dominating, then I have to go, I should also be close to the microphone, I remember. I cannot walk. You see that the two dominating point defects is the electrons and the oxygen vacancies, which was formed from this equation here. You also have, this is acceptor dope Syria. So this is the constant concentration of the acceptor dopant, which we on purpose put into the Syria. So as you go up in partial pressure oxygen, what happens then? You oxidize this and you go the opposite direction. So you remove this as you go up in PO2. So then the concentration goes down, and you see that there are other coming up. You have some interstitial, which is not really influenced in the beginning. Then you say that the electron holes are coming up, and if you go high enough in PO2, you see that suddenly the concentration of the electrons and holes, they are switching. In this window here, you see that there are only two point defects which is dominating. All of them are present, but the concentration are low except for two of them. That is the acceptor dopant and the oxygen vacancy. And you see that because of the charge, the concentration of the oxygen vacancies are half the concentration of the acceptor dopant. And here we really are in a good situation for one specific purpose. And that's to have a high ionic conductivity. So this is the window of the electrolyte. So if you have ceria as an electrolyte in a fuel cell, for example, this is the area you want to be. Here you can control the point defect chemistry, and you can control that the most dominant vacancy are the acceptor dopants, which are immobile because it's a cation, moving not so fast, and the oxygen vacancy, which enhance the oxygen transport properties. And so in this case you have a perfect electrolyte. But if you move outside the window, you will lose that. So if you, for example, would like to have a membrane or an electrode in a fuel cell, you would like to have both ionic conductivity and electronic conductivity. And one of the areas to be located in is the green area here, where you see that the two dominating point defects are oxygen vacancies and electrons. In this case, you have both transport of electrons and oxygen vacancies. So this can actually work as an oxygen pump in a way that if you have a high PO2 on one side and a low PO2 on the other side, oxygen will actually go through the lattice. And you can, for example, separate oxygen from nitrogen in the air. And this is also a proven technology, that you have oxygen around the membrane. You could also be on the other side here, where you also have a mixed conductivity, but in serial this is the two most natural regions. So if you are going to high enough PO2, you could even obtain oxygen interstitial in serial, at least from a theoretical point of view. In reality this doesn't really happen much. So that was the so-called Brouwer diagram you can use for ceria or fluoride structures. The nice thing is that they look fairly similar for the different stoichiometries, but for every stoichiometry, every lattice you have to work out the Brouwer diagram to understand completely the point defect chemistry. And this is not easy to do. It's a lot of hard work in order to get such a nice Brouwer diagram. Okay, then I will also just tell you that oxygen non-stoichiometry in perovskite is quite well known, but not necessarily in the ferroic community, but more in let's say in the solid state chemistry community. And this is an example, an old view graph, who kind of summarize some of these features known in literature. And here again you see that it's the delta in the stoichiometry here. Delta meaning the number of oxygen vacancies in the perovskite structure. So you can go from 3, 0, which is the perfect ideal lattice with a 1, 1, 3 stoichiometry between A, B, O3. And if you go down, you have oxygen vacancies. And you can see that the oxygen vacancy concentration here can be very, very low. Up to 0.25 in oxygen deficiency. This is 3 well-known perovskites, which are quite often studied as electrolytes in, electrodes in fuel cells. Lanthanum strontium manganite, lanthanum strontium cobaltite, and lanthanum strontium ferrite. And you see all of them has the possibility, if you go either they are the oxygen deficient, like if you acceptor doped lanthanum ferrite with strontium, you see that already at fairly high PO2, the concentration of oxygen vacancies are quite high. If you start to oxidize, it will go up, but still you'll never reach 3.0. So this material here is always oxygen deficient. If you go to the lanthanum manganite, it was the first electrode material which NASA introduced when they have fuel cells already in the late 50s and 60s. They used lanthanum strontium manganite. And the funny thing with lanthanum strontium manganite is that it can be both oxygen deficient but also oxygen excess, or in other words, cation deficient. Meaning that you can have a large amount of cation vacancies in a fairly perfect oxygen lattice, which is kind of more hard to comprehend. And it's not so many systems which show this behavior, where you actually have more oxygen relative to this ideal stoichiometry. And it's in a way kind of stupid to say that it's 3.5 or something. because it doesn't make sense. So normally you have to then renormalize the cation stoichiometry to less than 1. But that's hard to write and hard to calculate, so people normally do that with 3 plus delta instead. But there are not many examples of that in literature. This is one of the most classical. The other one is the cobaltite. You also see that it's very easy to get oxygen vacancies. And it's very steep. It's much more dependent on temperature than compared to some of the other examples here. But there are extreme cases in the perovskite family where the oxygen stoichiometry can go even down to 2. That means that 1 out of 3 oxygen positions are empty. And they are the best oxygen conductors we know. Okay, so this is the possibilities to play with chemistry. And especially if you have transition metals, and especially 3D transition metals, you have to take care of what's going on. There are some other interesting phenomena taking part at the same time as you introduce these oxygen vacancies. And one of them is called chemical expansion of oxides due to the reduction of the valence state of transition metals. This is one of the examples I showed you in the previous graph, Lampton-Strontium ferrite, where you have a dopant level or a substitution level 0.3, 0.4, 0.5, to 30 to 50% strontium on the lanthanum site in the lanthanum ferrite. And what I've shown here is the unit cell as a function of temperature. This is measured by the X-ray diffraction. And we did this in 2 different atmospheres, in nitrogen and in oxygen. And nitrogen, if you are lucky, the partial pressure of oxygen could be down to an order of 10 to the minus 6 in PO2. While in air, you know that the oxygen pressure is 0.2. So when you are doing the same experiments in 2 different atmospheres, and you know that there is a metal which is sensitive to the atmosphere, you see that also the unit cell of this system is quite sensitive to the level of dopant or substitution, and also the atmosphere. And the peculiar thing is that the valence, the unit cell seems to be not so dependent on the substitution level when you reach the reduced state. So the point here is that the unit cell is expanding when the transition metal is reduced, meaning that the oxygen vacancy has a different size relative to the field lattice. And the funny thing is that it doesn't collapse by making a vacancy, it's actually expand. Isn't that strange? You're taking out something and the lattice expands. First time I heard, I think, no, this is wrong. Can't be. But it's actually true. And the reason why it's like this is that you actually change the strength of the bonds in the material by taking out oxygen. You reduce the bond strength, and that's why the lattice expands. And here it's just illustrated what's really going on is that you have a mixture of iron 4 plus and iron 3 plus, and then the charge or the amount of iron 4 plus is then of course going down as you go down, up in temperature and down in partial pressure. So when we did all the experiments in pure nitrogen, we ended up with pure iron 3 plus in the lattice. Yes?
So you're saying that the strength in the material changes.
Sorry?
The strength changes, the bond strength changes. So you see your modulus also to be changing?
Yes.
So that confirms if it is an electromechanical system, then it should be softer.
Yes, that's also been shown. Okay. Good question. Okay, then we move on to the other thing which is also very difficult to control, and that's the volatile oxides. I tried to summarize this in a figure where the typical volatile components, and this is bismuth, potassium, lead oxide, sodium oxide, and so on. And the point here is that the partial pressure of these oxides is going up with temperature. And when you reach temperatures, let's say between 800 and 1000 degrees or even higher, where the typical processing temperatures we use both for bulk materials and thin films, you see that the partial pressure of these oxides become significant. If you set some kind of a limit that you see around 10 to the minus 6, you start seeing this influencing when you do bulk synthesis. And you see that all these partial pressures are above that critical limit, meaning that you're losing components during processing. The most well-known example is lead oxide, in PCT and lead titanate and so on, and in many other lead titanate-based ferroelectrics. What's happening is that you have lead on the lead side and oxygen on the oxygen side, and you create two vacancies and PBO oxygen gas, meaning that the lead oxide disappears. And that's also one of the reasons why we don't want lead in waste, because today, what do we do with waste? We burn it. And if you burn waste with lead, it basically will make lead oxide volatiles. And this is very poisonous. So you should not put your lead batteries in waste. So this is what's happening, and of course when you lose one of the components in your material, you create vacancies. And the vacancies we create when lead is disappearing is not necessarily the lead which is problematic, it's the oxygen vacancy, as I will tell you later today. So this can have detrimental consequences. And one cute little example of that is when you do grain growth in lead titanate. This is a work we did a few years ago in Trondheim. So then we looked at solid solubility of lead titanate, and I was particularly interested in this lead to titanium non-stoichiometry, because we had problems to know the stoichiometry we ended up with when we did the synthesis of this lead titanate. So what we did was to do a very careful study by changing the lead to titanium ratio, and we measured the tetragonality of the system. We know that lead titanate is one of the most it has the highest polarization of the oxides, a very high Curie temperature, and also a very high tetragonality. And we measured this carefully as a function of this titanium to lead ratio, and we also did looked at the lattice parameters and the tetragonality. And we do this quite and we see that there is a change coming from titanium excess to titanium deficiency. What happens is when you lose lead, you make those two vacancies, Pb and oxygen. Or if you dissolve titanium into lead titanate, you obtain the same type of vacancies. Lead vacancy and oxygen vacancy. And what we found from this the work was that we could control the cation non-stoichiometry in this fashion, that the X varied from 0.06 to 0.01. So quite a large lead deficiency is stable, while titanium deficiency we could not find any evidence of. And what is the consequence of this particular defect chemistry? If you did the same solid state synthesis of the material by changing this ratio, we saw that by changing the ratio from being a little bit of lead deficiency, lead excess, to lead deficiency, you see that the microstructure changed dramatically. So if you have a little bit of lead excess, you have an exaggerated grain growth, getting very, very large grains, and it actually densifies. So this is also, we measure this change in the disk during firing. So if you have a densification, you then have this larger than 0, and if the pellet is actually swelling, it expands, it becomes negative. And when we change the stoichiometry here, we come from sintering on one side to swelling on the other side, just by changing the overall stoichiometry with a very small fraction. So how can we understand this? Why is it like this? So the hypothesis is that we say that titanium oxide is soluble in lead oxide if you have lead oxide excess, or in lead titanate, but not vice versa. So this means that when we are looking at mass transfer through lead oxide flux, when you have lead oxide excess, you can actually get, for example, in a thin film, you get 2D film growth, you get a nice film. If you have lead deficiency, you will not have this, and you get coarsening, meaning that you're just going from small to larger particles, as you did when you have this swelling phenomenon. So just a small difference in cation stoichiometry makes a huge difference in the processing of the material. And of course, if you are a student and you are asked by your supervisor to make a sample like this, and you are not so careful with the stoichiometry, one student will end up with this one, and another one will end up with this one, and both would claim that it was a one-to-one stoichiometry, wouldn't they? So that's the problem. So in some cases, it's not so dependent on the stoichiometry. In some other cases, it is very, very. So if you have problems to make a dense sample it's probably telling you that there is something going on with the defect chemistry. Okay. Now I just want to stress what I already stressed several times, that oxygen vacancies are important in functional oxide materials. And it's the ionic defects, which is often referred to explain various phenomena. It often only said oxygen vacancy. But the point here is that oxygen vacancy is charge relative to the perfect lattice, and you need a charge compensating by other point defects. So if you are working in a system where you believe that the oxygen vacancy plays an important role for the functional properties, you have to look for another point defect in addition. There are several possibilities for charge compensation. One is the cation vacancy. That was the Schottky defect we learned earlier this morning. You can have acceptor dopants. As I told you in Syria, putting samarium oxide in Syria, you get the oxygen vacancy concentration, and you can, so that then the charge compensating species is the acceptor dopant. Here it was the metal oxide vacancy. Then you can have electrons, which is either delocalized or reduced transition metals, which is localized electrons. Two examples of that. In Syria, you get the delocalized electrons, and you get electronic conductivity, typical band gap conductivity. And in lanthanum ferrite, you get iron 2+, which is the charge compensating species. In this case, the electron is localized on the iron, and you get polar unhopping mechanism. So in all those four cases, the oxygen vacancy are charge compensated by another point defect. And that's very important to remember. And very, very often neglected in the literature. Okay, so now we have been working, going on quite a long time on point defects and point defect chemistry. I just have to check the time. Okay. And if you now look at diffusion of the ions, and if you have oxygen ions here, you have a hopping mechanism, which is dependent on the vacancies. The self-diffusion of oxygen ions depends on the vacancy diffusion coefficient and the concentration of the oxygen vacancy. So the tracer diffusion is actually dependent on the vacancy concentration and the diffusion of the vacancy itself. Often we think it is the ion which is moving in a way. So defect chemistry is paramountly important for the mobility of vacancies. And this is a field by itself. You can work on here, same equation in a way. You can elaborate a little bit more on it. But at the end of the day, you end up with something like this, which is an Arrhenius, where the vacancy diffusion coefficient is a pre-exponential factor times an exponential factor, where you have the migration entropy, which is easy to measure if you measure it carefully, or you can even today calculate it by density functional theory. And I'll come back to that in the end. So this equation is quite important. So here is an example of the oxygen diffusion coefficient and this is kind of state-of-the-art data, even though the reference here is quite old. You see that here is all this fluorite and perovskite data which are available in the literature. And you see that the oxygen vacancy diffusion coefficient here is not very different from the different systems. And there are two, so it's more dependent on the lattice than actually the concentration or the composition of the sample. And you see they are not very, very mobile, meaning that the vacancy diffusion coefficients are fairly low, even though we can still make technology out of it. But you have to go quite high in temperature. Normally you see that there is a trade-off somewhere when the concentrate or the coefficient becomes in this area here, you can start making technology out of it. And you see also that the activation energy, which is the slope of the curves here, is not very dependent on the different system. Even the diffusion in fluoride system, which is Syria or zirconia, are not very, very different from the one you have in the perovskites. So if you're interested in the oxygen diffusivity in another material, for example, if you know it's a perovskite, you can at least use these data as a first guess of the mobility of the oxygen ions. But also remember that cations is important, as we talked about in the Schottky defect equilibria. Then you also have to have cations moving. And the cations can move either on the surface diffusion, grain boundary diffusion, or bulk diffusion. And the most important take-home message by this slide is that there is a huge difference in mobility for cations if you're on the surface, if you're on the grain boundary, or if you are in the bulk. This is an example of 3 oxygen permeable membrane materials. which I've been working on quite a lot over the years. And we did measurement of the surface diffusion, which is given by here, up here. So you see that the diffusivity on the surface is very, very high. This is the bulk diffusion of oxygen in the material, because of the oxygen ion conductor. And this is the cation mobility in the bulk. And you see here is the orders of magnitude in difference in mobility. On the surface, we cannot distinguish the ions moving. So here is the unit cell moving. So we don't know if it's the cation or the oxygen moves faster or slower. But we only measure the slowest moving species. But still it's very high. So on surface, things are moving very fast compared to the bulk. The same applies to BSCF, barium, strontium, cobalt, iron is this perovskite. And again, you see that the cations are moving much, much slower in bulk compared to the surface diffusion here. So again, when you're doing processing, remember that cations are moving much faster on surface and grain boundaries, while in bulk they are quite slow. The driving force for diffusion is normally thermal fluctuation, meaning that higher temperature you will then, on average, have a longer diffusion length scale. But you can also have diffusion due to gradients in chemical, in electrochemical or electrical potential. So this means that in order to understand movements of, for example, point defects, you have to know if there are gradients in the partial pressure oxygen, if there are an electrochemical potential or is an electrical potential. And in ferroelectrics we know that point defects move, for example, even at room temperature in electrical potentials. But again, you have to understand the movements going back to the fundamental principles of the diffusion, which is again related to the vacancy diffusion coefficient. Okay. If you then look at the electrical conductivity, you have to take into account all the different mobile charge carriers. And normally the conductivity you measure is the sum of the contribution from all of them. So you have to know that the key pointer is the mobility and the concentration, because the conductivity is a product of the mobility and concentration. In some literature, the mobility is given by me, the Greek letter me. Again, several different nomenclatures appear in the literature. Okay, so that was the take-home message. In order to understand the concentration, you have to understand the defect chemistry, because that's related to the number of vacant sites. The mobility is a completely different scientific challenge, and I will not cover in this talk how we can measure the conductivity, but there are many different ways to measure the conductivity and relate that back to the mobility. Maybe the most fascinating thing is to use, as we did here, to use tracer diffusion. This is tracer diffusion data, where you oxygen 18 in an oxygen 16 lattice, and you can then measure by SIMS the oxygen diffusion profile, and you use fixed second law, and you fit it to the data, and you can extract the diffusion coefficient fairly accurately. It's a lot of hard work though, not easy. But you end up with reliable data at least. Okay. Then we'll go back to some examples. Maybe I have too many, so I'll have to keep track of time here. And I don't see anything anymore, because I need glasses. Yeah, so I have 25 minutes more to go. So let's see, at least we can cover the most important ferroelectrics materials. So if you start with the PZT, it's also the system we understand maybe the most. You all know that this is the state-of-the-art ferroelectric and piezoelectric material. And the point defect chemistry, or the defect chemistry, is so well known that if you look into literature, everyone knows, or the literature is very clear that if you have a hard PZT, meaning that you have a wide hysteresis loop, you have accepted doped PZT. And you can obtain a soft PZT by donor doping, typically niobium. And again, as I said, the most important issue here when you do the processing of bulk ceramics is the volatility of lead oxide, where this point defect equilibria is then the dominating one. So when you process PZT, you always have to take into account that you are creating oxygen vacancies and lead vacancies. And the question now, or the trick now, is to link the concentration of these two guys and the concentration of dopants to the electromechanical performance of PZT. So I try to simplify this by trying to explain what's going on when you do a donor doping and by acceptor doping. And I used niobium and iron as the two examples. So let's start with the soft, which is maybe the most complicated and most difficult one. When you dope niobium in PZT, you normally replace one titanium or one zirconium by one niobium atom. And then you have to remember that zirconium and titanium are 4-valent, meaning that you write titanium 4+ or zirconium 4+, but niobium is 5+. So it has one higher oxidation state. That's also why you have, when you look at niobium oxide, the stoichiometry is Nb2O5. So you can read the oxidation state from the stoichiometry of the oxide. So when you do then dope niobium into PZT, you then kind of dope in the stoichiometric amount of lead and niobium. And since niobium has one extra oxygen here, you have to start with an oxygen vacancy in order to make that apply. And when you do dope them, you annihilate, to take away one oxygen vacancy, and you end up with lead on the lead side, niobium on titanium side, which is a charged point defect, and then oxygen on oxygen side. So again, we don't create or we don't annihilate any charge, because we started with a double charge here and you end up with a double charge here. But the take-home message is that by niobium doping, you can reduce the oxygen vacancy concentration. That's the whole point. So by doping in niobium, you reduce the oxygen vacancy concentration. The opposite is the case when you do acceptor doping. Iron oxide, again, 3-valent, look from the stoichiometry. And when you do the same kind of equation here, you see that you get iron on titanium side and you get oxygen vacancies. So the whole point with donor doping and acceptor doping is to enhance or to decline the oxygen vacancy concentration. And what's known in literature is that the hardening or aging is related to the oxygen vacancies and the acceptor dopants. So how can you understand that? It's a very nice review coming off a few years ago, which tried to explain aging and fatigue in ferroelectric materials. And this nice figure illustrates 3 of the models, or the phenomenological models, trying to explain, for example, aging in PZT and other materials. And in all 3 cases, it's the oxygen vacancies which are the bad guy, so to speak. And I will go through the first model quite thoroughly, which is called this volume effect, where you are talking about how the oxygen vacancy, how it is oriented and how it is located relative to the acceptor doping. There is also some model or a phenomenological model called the domain effect, where it is the oxygen vacancies are accumulated at the domain walls, meaning that you are pinning the domain walls, because it's an interaction between the oxygen vacancy and the domain wall. I will not go into detail in that model. And the third one is the accumulation of oxygen vacancies at the grain boundary. But I will start with the one over here, because this is more related to the bulk or to the defect chemistry which I've been talking about. These 2 are a little bit more sophisticated models, and also here it's not so clearly how the oxygen vacancy are charge compensated, but it's again related to the mobility of the domain walls. But let's skip the 2 others and concentrate on one of them. I don't say that one is more correct than the other. And the point with the volume model is what we call defect associates. And that is an association, like a chemical bonding between the 2 vacancies. And you have that for vacancies or point defects with different charges. So in the first figure here, this is a very nice work by Paul Arart and co-workers who've been working with this phenomena from the DFT, that's the functional theory. If you look at the perfect lattice, it looks like this, and if you then have an oxygen vacancy, you can either put it in the AB plane, which is then perpendicular to the polar direction in the model, in the system, because the polar direction in the unit cell is along the z-axis. meaning that you have two different positions of the oxygen vacancy, either in the AB plane or in the C, along the C-axis. If you then have the lattice polarization going in this direction, you will then have three different situations depending on, if you can say that the acceptor vacancy makes appear, so M on the B side here is the acceptor dopant. You then have a kind of a polar or a dipole dimer, either pointing down when you have the oxygen vacancy here, is perpendicular to the field if it's is in the AB plane, or here it's in opposite direction of the polarization. So the main point here is that the hypothesis is that these three configurations have three different energetic states when you have the polarization pointing down. And the point here is, or the hypothesis is that this is the most sorry, one of them are the preferred orientation because of the electrostatics. So what they did is they used DFT to look into all this configuration, not only to the energy of them, but also how the energy or the transition state between the different configurations. It's a really thorough work, so I will go quite fast through it. So what they do then is to, they first of all they have carried out all the energetics of all these different configurations, so they know the energy of formation of all this, from the free oxygen vacancy to the different pairs I showed in the previous graph. And then they also looked at different transitions. So if you move the oxygen vacancy from one position to the other, you can see that there are many different paths, also depending on which the direction of the field. I will not go into all this, but they are labeled in different names for the different transitions or the different diffusion path. And they have been calculating this for the free vacancy. So you can see that moving the vacancy from the AC up to the C has a much lower energy relative to moving the vacancy within the AB plane. That's intuitively quite easy to understand. But then if you now introduce this acceptor doping, and they did it for both copper, which is one of the acceptor dopants well known in literature for PCT and barium titanate, and also for iron. And they also played with the charge of the oxygen vacancy. You can also do charge plus 2 and plus 1 in this case. At least you can do that in DFT. And you then look at the energy for all these different transitions. And the higher number here, it's a lot of details, but that's not even important. But the point here is, if the number is low, then this diffusion path is more likely to occur because the activation barrier is lower. If the number is high, they are slower and maybe it doesn't really happen. So if you take all this information, both the formation energy and the kinetics of the transition, you can end up with this very nice view graph, what's really going on when you make a sample. So in the DFT, you play with the play, and you say that you are making a material and you start observing the distribution of the oxygen vacancy as a function of time, starting with a random distribution. So if you look at this data, you see that, I know I have to move a little bit. Look at the concentrations here, that's the important thing here. So in the beginning, the material is dominated by the oxygen vacancies in the AB plane, has much higher concentration than on the C, and that's naturally because of statistics. The first relaxation happening is that the vacancy moved to the VC position, because that's energetically more favorable. And then you see that the dominating species is this free oxygen vacancy. But then the next happening at a longer time scale is the trapping of the oxygen vacancy. They're trapped by the acceptor dopant. And then you end up with this complex point defect pair, which is which is enhanced or which influence on the ferroelectric properties. So by doing all the energetics here and all the kinetics, they are able to track down the relaxation time for going from a random distribution of point defects to the specific pairs which lock in the polarization. And doing that for both the situation for iron and for copper, they could then put in the characteristic time scale for all these processes as a function of temperature. And the time scales are given in hertz. So you see that if you go to very low temperatures here, sorry, no, I have to be, to go to low temperatures here, you see that in some cases, especially for copper, which is should be over here, isn't it? Yeah. So the time scale of this relaxation is fairly long, so it takes some time before the oxygen vacancy are trapped by the acceptor dopant. But you don't need to go high up in temperature. The other thing, the calculation also show that it does not really depend on the concentration of the acceptor dopant. But to make a long story short here, from DFT they could explain that in these two cases where you are acceptor doping, the configuration of the point defects will be something kind of summarized in this cartoon image here. But you see that after the preparation, you see that these micro dipoles are randomly oriented because all the point defects are randomly oriented. Then you start the diffusion processes, and the dipoles are aligning with the polarization direction in the domain. This is a domain wall. So you see that all of these small green arrows are now pointing towards the same direction of the internal polarization direction in each domain. And if you do these AC cycling of the material, you can actually so this becomes a hard material or an aged material. You can de-age the material by doing AC cycling in the material, and then you start to see some of them flipping. So it's possible to de-age material by using an electric field, AC electric field. So in order to, so the point here is with this model, you can explain this phenomenological behavior of PZT. So I've shown some data we measured a few years ago where you also looked at the mechanical response of the same material. If you look at this, is just all these are tetragonal PZT and this is romahedral PZT. So you see that for hard materials, you typically have this pinched hysteresis loop, showing that the domain walls or the domains are pinched, and you need quite a large field in order to switch them. You obtain the hard one. You can also make soft by quenching it, meaning that you have not applied a long time in order to reconfigure the point defects, and you obtain more or less the same as the soft material. The soft material will always stay soft; it cannot age. And you see the same behavior for the tetragonal again, that you can change it from soft to hard, or the hard material can become soft by quenching it, making it that you go up to above the QE temperature and then quench it down again. And the nice thing is that not only the electrical mechanical response shows this behavior, that you can change the soft and hard, but you see also that the compressive stress versus compressive strain is also that you see that the blue one here, which is a soft material, behaves in the same direction. And this is maybe related to the chemical expansion phenomena I talked about previously, that not only the charge but also the size and the volume effect of the defects plays an important role here. So this is also quite systematically that you can change the ferroelastic behavior and use the same phenomenology to explain soft and hard ferroelasticity. Yeah, I'm running out of time, so the last example I will take, I think I skipped boron titanate for now today. Then I'll go to the next last example, is bismuth ferrite. And we'll be looking at bismuth ferrite together with bismuth potassium titanate as a small substitution or solid solution of this. And bismuth ferrite is one of the most studied materials because of the multiferricity. But again, here the defect chemistry has been a matter of debate, and it's still going on. So what we did was to look into the defect chemistry of bismuth ferrite. And working with the same material in the SFC community for a long time, we kind of adapted what we knew from that into the bismuth ferrite case. In bismuth ferrite, again, it's the bismuth loss which is problematic, that you lose bismuth and oxygen during firing. In this case, it's bismuth, metal, and oxygen leaving the lattice. And again, then you have these two charged point defects, which may play a role for the ferroelectric properties. And then one of the reasons why this is important is that bismuth ferrite is a very hard ferroelectric material, very hard to see the hysteresis loop. So maybe this is something related to the point defect chemistry. Again, iron is a very special case compared to titanium, which is in PCT and barium titanate. And that is because you can change the oxidation state, not only to lower valence state, but also higher valence state. So you can go from iron 3 plus to iron 4 plus or to iron 2 plus. So it's much more complicated with respect to the defect chemistry compared to PCT. So you have to take into account not only the two vacant sites which you have here, but you also have to take into account iron either as divalent or four-valent. And this is, of course, an effect of the atmosphere. So you can change the iron oxidation state by changing the partial pressure of oxygen. And you can also do donor doping to reduce oxygen vacancy concentration in the same way as it applies for PCT. That's not this case. And you can also play with the cation non-stoichiometry. We have looked quite heavily into that, and bismuth ferrite seems to be fairly robust with respect to it's not a huge variation in bismuth to iron ratio. And of course, again, it's sintering procedure, which is very important because of the thermal history. So what we did was to put up a mass action type of model, where we are measuring the conductivity, total conductivity, which is a sum of the conductivity from ions, meaning oxygen ions, electrons and holes. And we, in this case, we just neglected the ionic conductivity of bismuth ferrite, which is probably wrong, but we did it anyway. And then we put up the two equations. Sorry for the symbols disappeared, or the right point didn't come. But this is the two equations with the redox equilibria involving iron. And then we have a loss of A side, so we have to take that into account. And then we have to have the charge neutrality principle. So this is the balance, charge balance and electron neutrality. And then we also have to have a mass balance for iron, for the three different valence states. We can then put that into one single model, and we can then model the electrical conductivity of bismuth ferrite as a function of PO2 and temperature. And what we can see here is that, and this has not been known before for bismuth ferrite, is that it has the same kind of characteristic feature as many other oxide material, is that you have kind of a P-type conductivity at high PO2 and an N-type conductivity at low PO2. I can show the same for bismuth for barium titanate, which I skipped, but it basically shows the same. This is the conductivity of barium titanate as a function of PO2. And here you see again that you have an increase in conductivity going towards air, or high PO2, and that is typically a hole-type conductivity. It goes for a minimum, and then it becomes an N-type at low PO2. So you change the dominating charge carrier species. So that was also the point with the bismuth ferrite, is that you could show that the P-type conductivity in bismuth ferrite is probably not very strong. It is not low. You don't need to go low in PO2 before you have a dominating N-type conductivity. And that was maybe the most important part of this work, that you can show that we have iron 2 plus or N-type conductivity quite playing a role in bismuth ferrite. And you can, it's not a very high PO2 where this minimum is normally located. If you take the same type of data, for example, for lithium ferrite, lanthanum ferrite, which is kind of one of the typical dopants in bismuth ferrite, the minimum is shifted much further down in PO2. So there is something going on with bismuth in this case. Bismuth is different from the rare earth. And I also said that we neglected the ionic conductivity. And ionic conductivity is normally identified by having a shallow minimum. If this minimum is very strong, that's a typical example for that the ionic conductivity doesn't make a big contribution. But it's quite a shallow minimum, meaning that oxygen ions are probably quite fast in bismuth ferrite. And we already know from the hypothesis that we lose bismuth, we know that we also have a higher vacancy concentration of oxygen. So it should not come as a big surprise that bismuth ferrite is actually a good oxygen ion conductor. So that was the bismuth ferrite. Then I will end by telling a short note on water in oxides, which is not well known for many in this community. If you have an oxygen vacancy, you can actually hydrolyze that vacancy, meaning that you take water from moisture, and you can actually fill the oxygen vacancies. And then you get two protons, OH, written like this. This is two protons in the material. And what we know, proton, what is that? It's a charged, small species. And most likely also quite mobile, meaning that if you have this possibility to have water in your material, it will influence on the transport properties and also on the conductivity. So this gives rise to large conductivity. And of course, why do we know this? It's because proton conductivity is actually an important issue. And there is an own field in the SFC community where you're trying to develop fuel cell based on proton conducting electrolytes. And this is the state-of-the-art proton conductivity as a function of reciprocal temperature for different electrolytes, sorry. And the best one is barium zirconate, which is not, if you look at PCT and so on, these are quite similar type of materials as we know in the ferroelectric region. And the conductivity can become quite high, so this is reciprocal temperature, so you see that up around 500-600 degrees, you get quite reasonable conductivity, proton conductivity. The funny thing is that the conductivity drops again at higher temperature. Why does it happen?
Water evaporates.
Because this is chemistry. You know what's happening at high temperature? Water goes off there again. So the concentration of the charge carrier decreased. So you always have a conductivity maximum because if you go higher in temperature, the number of protons in the material goes down. And if you go high enough, they completely disappear. So this is dehydration. But the point here is that you can have a significant conductivity due to protons in the material if you are not careful. And then it's also shown not too many years ago that you can even have proton conductivity in grain boundaries in yttrium-stabilized zirconia. You see here is the resistivity as a function of temperature, and you see that the resistivity drops as you go down in temperature. And this has been shown to be water absorbed on grain boundaries. In the material, people have been claiming that there is no protons. So be careful if you have water around, and water is around us always. Okay, so let's try to summarize. So I tried to show you that the defects in functional oxide materials are detrimental for the electrochemical, electrical and electromechanical properties. The effect of point defect is more investigated than 1D and 2D defects. And the populations of the point defects are dependent on cation stoichiometry, dopant concentration, temperature, thermal history, and final size. So thank you for your attention.
Do we have any questions?
I have a question regarding lead technique.
Yeah.
So you said when it is lead excess, there is a grain worsening, and when it is deficient, so you have smaller grains. And the difference in percentage of was around 0.5%. So
very little, yes.
So how do we detect that 0.5% changes in the concentration?
Very good question. How did we do that, do you think?
Well, I don't know.
Right? That's a very, very good question. And that's why we, because we don't know. So what we know is the relative concentration of the two. But we don't know when we exactly hit the stoichiometric 1-to-1 ratio. So that's why we worked on both on the very hard on the excess side and on the deficient side. The point was to see that we have a transition from being excess or deficient. But to have a very exact description where it was 1-to-1, we don't know.
Okay, thanks.
So you are saying that the oxygen vacancies are interesting for ion conductors. So this is about like processing the materials in equilibrium conditions, like you heat it up to a temperature and create these vacancies. What about plasma processes? Say if you can deliberately induce these oxygen defects at what temperature you want.
But I tried to learn one thing today. What was important when you have oxygen vacancies in a material? You have to have some charge compensation process. So if you use plasma, what would then happen?
So you lose.
You can use plasma enhancement, but normally what you do then is that you're introducing other defects which might not be very stable. So if you then make them, you can the lifetime of this situation can be very short. In some materials, you use plasma or similar type of high energy methods to implement other type of defects. But normally you then quench the material to a very low temperature, so the quenched in defects you have are stable. But if you want to have oxygen ion conductivity, you have to use the materials at elevated temperature, and you cannot trick the nature. If you are able to make these kind of artificial point defects, they will disappear. So the effect of the plasma will disappear.
Do you have any examples for where then there is an absorption of water on ferroelectric materials and the losses have been higher or lower or something?
There are examples where people have claimed that there is water involved, but there is not really. In most of the ferroelectric materials, the water absorption concentration is fairly low. It's very hard to characterize that it is water and has the properties of protons. But there are in many works you have a clear kind of an indirect evidence that water is an important part, at least for leakage currents and so on, especially on surfaces.
Okay.
But there is no, not to my knowledge, very, very good works which really show that this is the case.
Okay.
But at least in films, the reason why I took it here is I think it plays a role, particularly in film physics and chemistry.
Are there any other questions?
Yes.
Short one, please.
Just one. By application of electrical field to the material, can we create an oxygen vacancy? What is the energy of oxygen vacancy creation?
That is depend on the material you have. So in the DFT calculation I showed for PCT,
Yeah.
they are similar to many other materials.
But we just distribute the oxygen vacancy in the material.
You can calculate the energy landscape of the vacancies at different sites, so you know the energy information of the different. And in some cases, the energy or the energy formation is so low that we also increase it, or we will induce vacancies by an electric field.
Low, just
It could be as low as 1.5 eV.
Oh, okay.
But it could also be as high as 5 eV.
Yeah, okay.
Yes. I had one question dealing with epitaxy. So if you fix somehow the lattice, you're going to affect the system to create this oxygen vacancy. So are you aware of any work dealing with strain dependence on this defects formation?
Yes, it's quite a lot of work, not so much experimentally, but especially from a theoretical point of view, where the defect chemistry, how it will be influenced by strain. And I also been involved in that myself, where you see that in some cases you can actually stabilize the vacancies by strain, either tensile or compressional strain, and it's also related to symmetry. So this is quite extensively studied by the functional theory calculus in the last 5 to 10 years. There are not many direct evidence experimentally showing that this is really the case. Only indirect evidence that you have oxygen vacancy playing a role. But again, often the charge compensating point defect is often neglected in these cases.
Okay, let's thank the speaker again, and other questions maybe over coffee.